A nuclear bomb attack occurred precisely at 12:01 a.m. in Orlando, Florida, at Disney World. Approximately 200 were injured and 400 were instantly killed. Sources say that a 30-year-old man named Hugo Jacari is involved in this accident. The search squad is currently looking for the suspect. For more information about the science behind the blast, let's have an interview with Marie Curie.
Hello, Marie Curie. Considering you've discovered radioactivity and discovered the elements polonium, radium and curium, can you please explain how radiation plays a role in this disaster?
First of all, radiation is a form of energy through which penetrating rays and particles are emitted by a radioactive source. Looking at the effect of this disaster, the situation is catastrophic. I can't imagine how high the radiation levels are.
Wow, Miss Curie. Alright, so how are people affected by radiation?
Radiation is detrimental to a human's health. It can increase the chance of a DNA mutation that can cause cancer. Radiation effects include radiation skin burn, blood count effect, and cataracts. This is fatal most of the time because it is extremely difficult to recover.
Oh goodness, that is not good. So anyway, thank you Miss Curie for your time and information. And now let's take a look at the James C.W. Hospital, where the majority of the victims are getting treated.
Hi, I'm Jenny Hill, and I'm live at the James C.W. Hospital. From the looks of this hospital, the injured victims are in a very bad state. Let's talk to Dr. Jones for more information.
Hi, so at this moment we are cleaning and bandaging the wounds. It is difficult to recover from radiation, as you can see, but there are ways to treat radiation, which is by using gamma rays.
Excuse me, but what are gamma rays?
Gamma rays are composed of high-energy electromagnetic radiation. They have a charge and a mass of 0, and they don't change in mass and atomic number. They have a high level of penetrating power, and they can either be stopped by lead or concrete.
Whoa, how interesting! Are there more rays like gamma rays?
Yes, in fact there are. There are alpha rays, which are composed of helium nucleus, and they have a positive charge. They have a mass of 4, but they change in mass by decreasing by 4, and they change in atomic number by decreasing by 2. Also, they have a low level of penetrating power, and they can be stopped by a sheet of paper.
Are there more rays?
Yes, there are beta minus and beta plus rays. They both have a moderate level of penetrating power, and they could be stopped either by wood or metal foil. They have a mass of 1/1837, and they don't change in mass. Their differences are that beta minus's atomic mass increases by 1, and it is composed of high energy electrons, and they have a negative charge. Beta plus's atomic number decreases by 1. It is composed of high energy positron, and they have a positive charge.
Thank you, Jenny, for that report. Now, more breaking news. We have received a clip from the bomb scene. Let's take a look.
Ah! Mom! There's a chemical bomb!
Wait! That's not a chemical bomb! That's a nuclear bomb!
What? What's the difference?
Chemical reactions occur when bonds break and atoms don't change identity. Also, they only involve valence electrons, and small amounts of energy is released or destroyed.
However, nuclear reactions occur when the nucleus emits particles or rays, and atoms transform into other elements. Also, they involve protons, neutrons, and electrons, and they involve lots of energy being released or destroyed.
Oh, okay. Ah! Mom! There's a nuclear bomb!
You're back with Lucy Scott. The suspect, Hugo Jacari, was finally caught. We have just found a clip of Hugo Jacari making the bomb. Let's take a look.
ha ha ha! At last, I can finally go through my master plan to seek revenge on Disney World for the trauma it caused me as a child. Now, I need to decide if I'm going to use a fission or fusion bomb. I should do some more research about how each work and go from there. Okay. Well, in fission, it is a uranium isotope that undergoes it. A fissile nucleus is split into two large fragments by a fast-moving neutron, and if controlled, energy is released slowly like in a nuclear reactor, and can be turned into electricity. Fission, simply put, is a nuclear reaction in which an atomic nucleus splits into fragments, usually two fragments, of comparable mass, emitting 100 million to several hundred million volts of energy. This energy is expelled explosively and violently in the atomic bomb. Well, I like the sound of that. Alright, moving on to fusion. In fusion, two small nuclei combine to form a single larger nucleus. It does not occur under standard conditions, and positively charged hydrogen atoms repel each other. At extremely high temperatures, the nuclei of the hydrogen isotopes, deuterium and tritium, can readily fuse, releasing enormous amounts of energy in the process. However, deuterium and tritium, the fuels for fusion, are both gases and are hard to store. Well, I guess that means I wouldn't be able to store them at Mother's house. Some advantages of fusion are that it is inexpensive and there isn't radioactive waste. However, it requires large amounts of energy to start reaction and is difficult to control. I think I'm going to use a fission bomb because it is easier to control. Now, I must predict the stability by using the atomic number. This element's atomic number is from 1 through 20, making the isotope very stable. Ugh, that won't do. This element's atomic number is from 21 through 82, making the isotope somewhat stable. That won't do either. This element's atomic number is greater than 83, making this isotope unstable. Yes, that will very much do. Now, I'll predict the stability by using the nuclear makeup. For odd protons and even neutrons, or vice versa, if the mass number is different by greater than 1 AMU from the element's mass, the nuclide is unstable. Excellent. For even protons and neutrons, if the mass number is different by greater than 3 AMU from the element's mass, the nuclide is unstable. Even more excellent. Finally, for odd protons and neutrons, everything is unstable except for hydrogen with a mass of 2, lithium with a mass of 6, boron with a mass of 10, and nitrogen with a mass of 14. Even excellent of them all.
Now, here's Sam Williams with the zone of stability map and the weather.
Thank you, news lady. Now, we can see that it's been a crazy day today. Let's take a look at our here map. There are quite different things going on here on our graph. First of all, let's take a look at our valley of stability. Our stable nucleides are represented by the black dots right there. You see them? Yeah, okay. So, now, when we look at the right side of our valley of stability, the nucleides are proton-rich and tend to undergo beta plus decay. And when we take a look at the left side of the valley of stability, we can see that our nucleides are neuron-rich and they tend to undergo beta minus decay. And when we have a very large nucleides, like we see here, they are near the top of the graph and they tend to undergo alpha decay. Also, when we take a clear look at our map, again, the shaded regions are where unstable nucleides lie. And, as for the real weather, it's probably gonna rain. Back to you, news lady.
Stay tuned for more information. I'm Lucy Scott, and I'll see you soon.